So in this section, we're going to be looking at a bunch of different ways to use Charm++, and a lot of them relate to language. And the first talk is going to be on Spectre by Nils Deppe, and you'll see how they have used Charm++ in a kind of novel way.
Thank you, Eric. I'll be talking about our code Spectre. It has a new face or a new interface. And so briefly what I'll do is I'll just give you sort of an update and tell you what Spectre is all about, and then I'll talk about what we've done with Charm++ to make it a lot easier to use and why we wanted this, or we needed this even. So Spectre, the goals is to be, we need a multi-physics, multi-scale code. So our collaboration does computational astrophysics. We simulate binary black holes, binary neutron star mergers, and star explosions. And so these problems tend to range in about 5 to 6 orders of magnitude or more. And so with that, we need a lot of microphysics and a lot of physics in there already. We need hydrodynamics, we need to solve the Einstein equations, we need radiation transport. So we need to be able to do this in a general and in an efficient manner. And we're also hopeful that since we need to implement all of these things, we can actually at some point find uses for them in other disciplines. One of the main things we've been working on over the last year is taking our private toy code and making it open source, available on GitHub. And the big targets is sort of, it needs to be efficient, and we need to get to exascale with this, because for experiments, so when we work with experimenters and they make a detection, they need us to do a binary black hole simulation in like 3 days. The current state of the art is 3 months, and so we need to get that down. And so the only way we're going to be able to get that down is by scaling our codes up. So what we've been working on, so this is what our current production code uses for the domain. So these spheres in the middle here are the black holes. There's a larger one and a smaller one. Outside, far away, you have these spherical shells. Then you have shells sort of around near the black holes, and then you divide up the domain here and get everything to connect. And so what we are doing, we're using discontinuous Galerkin, and so a graduate student has been working on implementing this using only cubes. So we basically take a cube and we deform it and twist them around so that we get this sort of connectivity. And so this is all pretty much in now. The last sort of phases where we connect out from the inner surface to the outer cubes is currently being implemented. To make things a little bit harder, with all of that is actually, we can't simulate the insides of the black holes. There's a singularity and our code would just blow up. So we actually cut out the interior of it here. So you can see here these surfaces. And so we need a moving mesh. We track the surfaces of the black holes during the evolution, and then as they collide, we change the mesh. And so this is for a mass ratio 9 simulation. So this black hole has 9 times as much mass as this one. And you see they're quite deformed, but they're not spinning. When they spin, they get even more deformed, and they kind of wrap around each other. So you get very, very deformed meshes around them, and we have to be able to keep track of that. And so there's a graduate student at Caltech currently working on this. We call it dual frames. If you're from an engineering background, it's the arbitrary Lagrangian Eulerian, ALE. And so it's basically the same thing. We just use it in the context of astrophysics. And the other difficulty with all of this is, so we take this domain and we map it back to this domain, but then we have to resolve the small timescales here and the far out timescales here. So another graduate student has been developing and has implemented a novel higher order local time stepping method that's conservative as well, because we need to do conservative hydrodynamics. So that's what Spectre is, kind of the current physics state of the code. And so the first problem we're going to be tackling is an accretion disk simulation, since getting all of this tracking working correctly is very difficult. All right, so now I'm going to be talking about our new interface. So our goal was to eliminate the Charm++ interface files. We found several issues with them while using them. We found them to be quite restrictive in the sense of, if I want to have generic code with templates or anything like that, I can do it, but it's not great, and there are some limitations. It used to be if I stick std array in a CI file, I would get an obscure error. If I stuck, double ampersands for R value references in a CI file, I got another obscure error. And so that was kind of not great. And this error-prone, this point is actually where we said, okay, we're just going to do something and write an interface to it. There was a senior research associate at Caltech and one at Cornell and myself. We spent together 6 hours debugging an issue in a CI file. It ended up, we just had to rewrite the CI files to figure out what was wrong. We got the correct and incorrect results, everything from seg faults to getting the right answer. Run it through a debugger, and we get somewhere in the depths of Charm++. We had no idea what was going on. It was just very difficult. The other thing is, more so for the Charm++ developers, but also for users, the CI files add kind of a maintenance burden, right? They have to figure out how to parse C++. And while I'm not a compiler engineer, I can appreciate that parsing C++ is really difficult. So if Charm++ developers don't have to deal with that, I think they would appreciate that. The other thing is, because with the way the CI files work, is you're kind of limited to whatever the CI files can parse. And so you miss out on some newer features of the language, such as perfect forwarding and move semantics. And this actually results in inline methods being significantly less efficient than they could be. So these inline entry methods is, if you have two chars on the same physical core, you don't have to copy the data, but you actually end up copying the data in some cases because of the way the user ends up using it, and it's not at all obvious to the user. And so our solution, if you saw my talk last year, you won't be surprised, it's metaprogramming. However, you might be surprised, there are not going to actually be that many templates here, because I want to propose an interface that a physics graduate student in their first or second year can use, not a computer science student. And so what we think is important for this interface is it needs to reduce user code. So the code that the users need to actually maintain needs to be less. It needs to be easier to maintain. I think that the next 2 points are most important. It needs to be really easy to use. This is, again, how do you convince someone to rewrite their application? Well, if the code is very different from, say, your MPI code, you're going to say, okay, well, I don't know. I need to learn the language. Like, what is a main char? And all of these things. It just makes it harder. The other thing is we can't stray too much, I think, from the current existing model in terms of message-driven objects you call entry methods, because then you have the problem of how do you convince existing Charm++ users to switch? It needs to be conceptually simple. So if it's familiar, it's easier to adopt. Same with if you're coming from an MPI perspective. If your new interface is, again, very familiar, it's much easier to change. The most important thing is also, I think, the code needs to be error-free. By error-free, I don't just mean you get the right answer, you get the most efficient right answer. So if something doesn't, if I do an unnecessary copy because Charm++'s implementation is not generic enough, I think then their code actually has an error in it. And ultimately, one of our main things that we've been trying to do is eliminate runtime errors. When Charm++ tells me, hey, something wasn't registered, it doesn't tell me much other than something wasn't registered. I don't know what something is. I have like 100 things. What do? I don't know. And so this is meant to be somewhat interactive. If you have any others, please tell me now, tell me after, write them down. I asked Sam and Eric to take notes so that these things actually get remembered, because this is something that I think can actually make people's life easier. So please interrupt, ask questions, and if you have ideas, contribute. All right, so the order here might seem a little bit weird. I'm going to first talk about invoking entry methods, then creating chars, and then reductions. So the way that you want to invoke a function is you just call it, right? And so let's say we have an entry method 0, entry method 1, and some Charm++ proxy called myProxy. This can be an array, a singleton, whatever. I want to invoke entry method 0, and entry method 0 doesn't take any arguments, so it's just a function. Then what I say is here charmxx is just a namespace I've given for Charm++ code. So this is something that would come from Charm. You say charmxx invoke my entry method 0 on this proxy. And it will just invoke that entry method there. That's it. If you want to pass arguments, you just pass the arguments along with it. There you go. That's your call. And so let's see, can we go to the next one? There we go. So then the question is, what does this entry method look like? Well, what we're trying to do here is piece together a class including member functions and member data from outside. So we need to sort of inject these things. And C++ probably won't support this fully until like 2026, and I don't want to wait that long. So an entry method changes from a member function to just a simple struct with a static apply method. So this is effectively a free function. The reason for making this choice, though, is if I have a struct with a member function that's static, this can be a function template. If I have a free function, I can't do the same approach. You then have to specify all of the template parameters to the function here. That largely defeats the purpose of templates, in my opinion. So here, it's my entry method 1. I pass it arg0, arg1, and arg2. See, arg2 here, it ends up being an R value reference, which just means that no data actually gets copied here. So if you call this inline or anything like that, you never have a copy. Like, you just steal that data over to yourself. And so, like I said, so here there's going to be a few confusing points. One is, well, these aren't really member functions anymore. And we need to deal with a couple things. How do we handle attributes? So inline, threaded, and these sorts of things. And where the heck's the member data? Right? Like, you told me I have an object. Where is that member data? So I'm going to talk about attributes first. I think there are two ways of doing attributes. And I think both are actually valid depending on what the attribute is. There are attributes, so I just use the inline in both cases, but for attributes where it only makes sense for this entry method to always be called with that attribute. Let's say you always want it to be threaded. That's just a property of that entry method. You specify it in the entry method class itself, and it will always be called that way. However, let's say I want to inline the actual function. I may want to only sometimes inline it. So sometimes I want to make sure that control goes back to the Charm++ runtime system. Otherwise, I can have things happen like I can blow my stack. So I say, OK, but other times I might want to call that same entry method, but I don't want to go through the Charm++ runtime system if possible. I want to call it locally. If the other char is on my processor, I just want to call it. I don't want to go through Charm++. And so this means that attributes would no longer be specified in a CI file. You no longer have to dig through the CI file and figure out, can this be called as inline or not? You just specify it at the call site. So these kinds of attributes, depending on what it is, end up in these two places. And
you actually want to support both, not just...
Yes, I think both is the right answer, depending on the attribute. So this, I think, makes sense for inline, and I think for maybe something like threaded, this approach makes more sense. So maybe. All right, so then the member data is the next thing. Those of you who saw my talk last year, this I would imagine as being something like a tag tuple. You can just think of this as just even a std tuple. You just have a heterogeneous container of data. And so you can then say, OK, well, so this is my member data. And so I now somehow need to tell my char what types should it hold. What will the member data be? And maybe I can pass that as a template parameter to the char. So basically, ck_new would create the char using something like this. It would pass in my starting coordinate and my starting velocity for my particle coordinate and my particle velocity. And so basically then what you can say is, OK, this member data, this std tuple, or this tag tuple, depending on whichever one you're more familiar with, will just get passed to the entry method. So what that means is, as I promised, there'd be one parameter pack, and here it is. The apply function takes as its first argument the member data. Right? So this is effectively then, this is the data that is what is currently stored inside your char, gets passed into your free function. You then retrieve, let's say, the particle velocity. You retrieve it out and set it equal to VEL in this case, and similarly the particle coordinate. And then I can update these. I can do my math. Whatever math you want to do would go in here. And here I've also passed in as an extra argument the time, so a delta t. And so this would be something that was invoked remotely. There's another approach that, with some discussion with the Charm folks, and I thought about it a little more, you could do is you could, of course, also say, well, if the only thing I'm holding on my char is what you now write as your implementation of the char, you could again just forward things to member functions of the only, so if the tag tuple only holds one element, one thing, and that thing is your class that has member functions and member data. You can just use these to forward to that. So that basically means you can take your existing code, and all you do is you write a little wrapper around it, and that's it. And so the idea is all communication and everything will happen in these entry methods. And you will generally farm out to user functions the actual work.
So that quad is not a set?
Quad?
Is it modifying the object's member data?
Yes, it's retrieving it by a non-const reference.
Oh, you're okay.
Yeah,
Okay.
yeah. So this is getting, the chord is getting retrieved by a non-chord, yeah, and then you modify it.
But note that this is roughly you're making the user write what the translator generates. This is where you're saying, if you get this, then call this method, especially if you pass in the tag of the object.
No.
Of course, you're getting compiler type checking. That's true. But
No, this is not
sorry.
code that is currently generated by Charm++.
No, I'm saying current compiler, current Charm CI translator will generate for each entry method the skeleton code which says when you get this envelope, unmarshal it and call this member function of this object.
Yes.
Right, and this is kind of analogous to that. What you said in the end, not this part.
yes,
yes. What you said in the end. If you the forwarding part that you said.
Yes. If you use the forwarding approach, it's analogous to that. If you implement the code directly here, then you're just using a functional
right.
case.
Correct. Yeah.
Right. So the idea is this is sort of where, let's say, your STAG code or something like that, in terms of here's where all your sends and receives go effectively in these entry methods. And so one thing that you always have to worry about when you start sticking everything in header files is what's going to happen to my compile time. And so for that, you can address it by saying, okay, well, I'll just stick all my user code into a CPP file, and then I'll just call that function there. So that literally all you have in the entry method is say, here, I get some data, I call the update, and then below here, I could have another charm invoke call, which would be your MPI send if you're more familiar with MPI. And so that means that the actual code that you stick in your header files for your entry methods is quite minimal and won't burden you in terms of compilation time. So then the update coordinate.hpp will have your forward declarations, one for doubles and one for vector. Vector here is just some expression template class that allows you to do math like you would on a double. And then if you wanted to change between them, all you have to do is you have to change the type that particle chord or particle velocity is, and you immediately get support for both of these. So you could run one simulation where all your coordinates are just doubles and another one where your simulation are all your coordinates and velocities are vectors, and all of the code has to basically stay the same. You could even promote this to being templates and do explicit instantiations to deal with compile time. All right, so that's invoking entry methods. The next thing we want to deal with is actually creating our chars. And so we need some way of identifying a char. So right now, the way Charm++ does it is you name a class in the CI file. So we need some way of naming what that type is. And if Charm++ only supplies one type, a char, and it takes just template parameters, then, well, the name will effectively be the template parameter. So I can write something called my char, and here I said my char name. So this is the name of the object. And then I give it some properties. So the first property is it a singleton, an array, or a node group? So you set that inside here. For arrays, you also have to specify an array index. So in this case, it's my awesome array index, because it's just that awesome, right? And so then you also need to specify your member data, right? So this is what I had several slides before being passed in to the char directly. So here you say, okay, please hold this as your member data. And then ultimately, this is something that Charm++ provides. This is the type of the proxy. So what this is necessary for is that you can actually make a char or a char proxy be part of your list of member data. So because typically, let's say if you want to communicate, you need a proxy to the other chars, and that means you want to be able to use the same name that you actually named the char as the thing in your member data that's holding the proxy. And so that's why you need this last thing, so that you can actually use that in here. And so then the way actually creating them would look is you say, okay, I lost a create here. That's not great. So here you would use my proxy create my char name, and then you have the start and chord and the start velocity, and then you can create a second one, my char name too. And in this case, you pass in, you say, okay, I want my proxy is start chord and the start velocity. So here you can see that you can then also pass around the other proxies, and you can retrieve them by their name. And so basically here, create is just what would be ck-new currently. And like I said, this char name is also the tag in the member data. So you can use the same name everywhere to grab out your proxies. And so the other thing that we found, and we actually got kind of for free, is Charm allows you to do custom array indices so that you can index it however you want. And so in our domain, we set it up via low resolution large blocks, and then inside of those blocks we perform AMR. And so we index things with a block, an X, a Y, and a Z coordinate, and that's it. And then in Charm++, you have to write all this overhead with placement new, the specific thing that is the size of 3 bytes, and translate all of these things into Charm++. And basically what Charm++ can supply, and should be supplying for you, is just a generic template, and all you have to do is you just use, say, in this case, I'm using element index. It's the size of the 3 ints that Charm++ requires it to be. And so I can just use this class to index my array. I don't have to write any extra code for Charm++. And so this you just kind of get for free along the way. So this makes indexing into arrays a lot easier. You don't have to write any conversion code or anything like that. You just write this thing, and then you just say up here, instead of my awesome array index, you use element index. And then you can index into it using that struct. All right. So then the last thing is reductions. And so reductions we've also simplified. And so what you have is you have a free function called contribute to reduction. You again pass it an entry method as a template parameter. And you say, okay, I want to send this data, my send double to array proxy, from array proxy my index to my target proxy, and I want to use Charm++'s product double, so I'm going to multiply them all together. And that's how you contribute reductions. That's it. Then when it's all done, it'll invoke this entry method on the target proxy. So then the other thing is, with Charm++, if you want to reduce custom data, there's support for this. But again, there's a lot of registration and overhead of getting custom data to be reduced. Like this, I found, was also a very painful thing to get right. And it turns out you can, again, we do that for you. We do all the registration and everything for you. All you have to do is you just say, okay, we supply to you some reduction data class. It has template parameters. And you say, okay, those template parameters, I want to reduce an int, a hash table of strings and ints, and a vector of doubles. That's what I want to reduce. You still have to write your custom reduction function. There's no way around that. Charm++ can't know what you want to do with the individual data. But here, you say, okay, I've filled my reduction data, so I'm sending the number 10, some map, and this vector. And then you just call contribute to reduction. You pass it a function pointer, the entry method, the data you want to send, where you want to send it, where you're sending from, and where you want to send it. And then it'll just do the custom reduction. The other thing that some people might care about, at least I will, is with this model, in C++17, you get const expr lambdas. In the current Charm++ model, you can't really take advantage of new language features. There's a little trick that you can convert lambdas that don't capture anything to function pointers, which means in C++17, where you have const expr lambdas, you can get a const expr function pointer. And all of a sudden, you don't have to write a separate function for this. You just write, if it's a small function, inline right above where you call the contribute to reduction. And there you have it. It'll convert it, and then everything will work just fine. Everything still gets registered. And so one thing I want to say is this is not a dream. We've implemented this. This works. We use this. This is what our code does. This is the interface we've built. We have 4 CI files that we write. We run them through Charm-C. We post-process them to fix a couple minor bugs, and then we use this. I am the only person over the last year who's looked at a CI file in our group. Everybody else just uses that interface. They get compiler errors when anything goes wrong. Everything gets registered for them. Instead of spending 4 hours trying to get a new executable, you spend half an hour, 20 minutes. It just all works for you. And so here what I said is we've replaced Charm++ interface files with basic metaprogramming. The big emphasis here is the basic. If you're comfortable with sticking a template here and there, this will work for you. It's not reasonable for me to expect somebody, a first-year grad student in physics, to be able to understand what all this crazy templates is doing. I think I can expect that from the Charm folks, at least someone in the group, but not from physics students. And so this is the thing. Users don't need to do anything special. You just call functions. And even if you're coming from a Fortran background, calling functions is something you do there too. The big thing is we've eliminated a huge number of errors. Hey, you didn't register some entry method? I can't remember the last time I saw that because mine just get registered. I don't have to worry about it. And so there are still a few things you can do wrong, but you get the errors at compile time. Compilers are generally much better at parsing C++ than anything that somebody who's not a compiler engineer can put together. And so typically that's actually a quite reasonable way to do this. And I've been talking with the Charm folks to possibly integrate some interface like this into version 7. Not to necessarily replace CI files right away, but to allow people to explore this kind of thing. And the other thing is, if you want to use this, get in touch with me on our GitHub. It's a CMake file and 2 header files, and then you can use the same interface in your code. And the CMake file, all it does is run sed over the HPP files. So you can integrate that into your own build system. So yeah, that's all I have to say.
One slide.
Yes.
First of all, very nice talk, and there is a persistent demand for .ci file. I can never put my finger on whether the aesthetic that people have for what they want will permit them to see this as more elegant. I mean, it's very subjective, but I think it's definitely the fact that there is no .ci and therefore no double jeopardy of your syntax errors and so on is very useful. So I'm very hopeful about this. Let's see what the user community does with it. The narrow question I had on this particular slide was, why do you need the from array proxy square bracket my index for the sender, for the contributor?
Because normally you call this .contribute or this arrow contribute.
Oh, that's right. Okay. Yes. So the system knows in our case who the contributor is, so it can track. Okay, got it.
Yeah. And so basically, because you no longer have a this, since entry methods are no longer member functions, you need to pass that information in somehow.
Yeah, and if you go back a few more slides, which is kind of the main thing where you're describing an entry method, how an entry method is defined.
This one?
Maybe, this one. So this is where we were debating earlier about, so another way of writing this would be I'm one of the Charm++ users who wants to see my objects as C++ classes. Then I would write my char class, and all that I would do is I have this polymorphic function, apply function here, and I would make that apply function call my object's entry method. It won't be entry method anymore, just a method that corresponds to that. That's a legitimate usage pattern?
Yes.
And is that something that people do often enough in your group, for example?
So we've opted for this approach. That's what we use mostly. But what that would basically look like is you would do get my object on member data and then dot whatever your member function is. So we personally don't use it. We're happy with this interface, largely because for us, intro students typically have, say, a Python background or a Fortran background, and so they're not coming from an object-oriented background. But if you are coming from an object-oriented background, I don't think that's an issue. And I think you can even actually provide an alternative method around this where all you have to basically do is tell, instead of passing a struct, you pass a function pointer into the object.
Yeah, because what I'm thinking is an intermediate approach which is a bridge between the two, where you would get all the other things that you get with Charm++ objects, maybe entry method tracing and so on,
Yes.
by providing some kind of automating generation of this function given that object, which would be like a translator, yes, but
Yes.
it will be a lot more type checking than the current scheme allows.
Yeah, I mean, basically all you have to do is you have to provide some way of saying at the call site, you have to give invoke something that it can invoke on the thing.
Right,
So let's
right.
say instead of having a tag tuple, if you just had an option to say, okay, this could be, instead of, where was it? Here you say tags, you could say this is, say, object equals blah. Then you can instead pass around, say, function pointers into that object. And you pass that to invoke, and then Charm++ can generate the through entry method call because it knows what function to call in the object.
Right.
So I think with this you can have both interfaces and both work together, and I don't see there any issues.
So as Sanjay was talking there, I just noticed this slide actually has a bug. You have undefined behavior because there should be conditionally no except on update coordinate, right? So there's.
Sure, I don't have enough room to put no except here, so there's not.
But now
a
you're
bug.
requiring the user to remember that anything called and apply needs to be no except, right?
Sure, but this was user written code anyway, so that's their problem. That's not Charm++'s problem.
Okay. Well, I was just
And
curious.
so worst case scenario with this, what you get is you get a std terminate, which means that your program exits. And honestly, if I can't update the coordinate correctly anyway, I would expect that my simulation should terminate.
Okay. Sorry, the microphone just turned off. So yeah, so it's just undefined behavior essentially.
No, it's not. It's perfectly defined behavior in the language.
Yeah, so it calls to terminate, which can do whatever it wants. Yeah. The other question I had was for create. Do you have plans to allow it to accept custom allocators?
You can't currently use custom allocators in Charm++.
At all? Oh, okay.
So if the Charm folks want to support custom allocators for that, sure, but
Okay. Okay.
all right. Oh, my water bottle.
Nice. Sorry.